Okay, so I forgot to turn my mic on this morning, so I have to record you guys this time. But that's okay. You guys asked more questions anyway. No, it just was dead. There was no sound. It was just me scribbling. Okay, so what we're going to go over today is work energy theorem. Good news, you learned this last year. Okay, we're going to, basically everything we do today will be a review of the concept, and then we'll start working on a few problems that are more physics 20-ish than they are science 10-ish. Okay, so first thing, and this doesn't change, is what work is. All right, if work is being done, okay, then mechanical energy is changing. All right, that's what work is. Work is a change in mechanical energy. Now, what makes up mechanical energy? Okay, well, force makes up work. If I exert a force through a distance, okay, that's going to cause work to happen, right? Because you learned in Science 10 that work is force times distance, okay? That was your Science 10 formula. Partly. What two things make up mechanical energy? Two types of energy that make up mechanical? Kinetic and potential energy, okay? So, in Science 10, you would have only dealt with situations where the change in mechanical energy was one or the other. Okay, so you would have had a situation where a force accelerated a car along a level road, or a force lifted an object from the floor to a table at a constant velocity. Only one of the two types would have been changing in any problems you had in Science 10. So you would have had like force times distance equals EK final minus EK initial, and then you would have calculated something. So you would have had like force times distance equals 1/2 mv final squared minus 1/2 mv initial squared, and that would have calculated your change in energy. Okay, you would have only had one type of energy changing. In physics 20, we look at this the way it happens most of the time. Okay, and that is that the mechanical energy, both kinds, change. Okay, so I do some work, which is still force times distance, but now I'm going to be changing the mechanical energy. So that'll be mechanical energy final minus mechanical energy initial. And I calculate mechanical energy by adding the potential and the kinetic together. Okay, so I would have something like this. I would have EP final plus EK final minus EP initial plus EK initial. All right. Everybody okay with that? So all I've done is say, this is how I calculate mechanical energy, potential plus kinetic. And I would take the final values for these things. Remembering, and you learned this in Science 10 as well, that we calculate gravitational potential energy by going mass times gravity times height, and we calculate kinetic energy by going 1/2 mv squared. Okay, so we have formulas that we would plug in for these values. Okay, it ends up looking a little bit like your conservation of energy questions that you would have done, like the roller coasters, EI equals EF. Okay, so in a law of conservation of energy question, this and this are the same number. If work is done, they're not. Okay, energy is not conserved in a work problem because the energy is changing. Something is either doing work on something else or is having work done to it. Okay, so if it's the situation where I'm having work done on me, what happens to my mechanical energy? It goes up. Okay, work is a transfer or a change of mechanical energy. If work is done to me, then my mechanical energy is greater. The object that's doing the work on me is going to have less mechanical energy. Okay, it's transferring some away, I'm gaining it. All right, everybody okay with that idea? All right, so that's kind of what we're looking at. Okay, we could expand that out even further, okay, where we would say it would be like m times g times h final plus 1/2 mv final squared, okay, minus m times g times h initial plus 1/2 mv initial squared, right? We would have all those things. And the question then could ask you, if the work is done over 100 meters, calculate the force. Okay, so then I would isolate F. All right, or if it said this much work is done in joules and gave me a bunch of other information, I could calculate what the final speed of the object would be, or what the initial speed of the object was, or height, or whatever. I can calculate basically any of those variables as long as I have all the others. Okay, it works a lot like how you manipulated a conservation of energy problem. Okay. All right, so that's kind of what we'll be looking at today. Okay, so what's work? Work's a change in energy. Okay, very simply, work's a change in energy, which means that there's this thing with work and energy. You can't have one without the other. All right, so it's like December 15th or whatever, and your parents knock on your door at 6:30 in the morning. Hey, get out and shovel the driveway. It snowed 12 centimeters last night. Go and shovel the driveway, and you're like, I have no energy. I can't do that. I mean, you're lying, because if you had no energy, you'd be dead. Okay, but if it was true and you had no energy, you'd be absolutely right. You would be completely incapable of doing any work like shoveling the driveway. Okay, because that would involve you transferring mechanical energy from yourself to the snow. Okay, moving it around, changing its position, changing its velocity, all that kind of stuff. Okay, that's work because it's changing the energy of something else. All right. But that does kind of bring up, well, I hate using this analogy because it's dumb. Which came first, the chicken or the egg? Okay, which came first, work or energy? Like, well, with work and energy, that's actually a tough question because you can't have energy without work and you can't have work without energy. But the chicken and the egg is dumb. Clearly, eggs came first. Right. See, birds evolved from reptiles, and reptiles lay eggs. So clearly, eggs came before chickens. Dumb question. Dumb question. Eggs came first. The first chicken was born from something not a chicken, and there was some random mutation that caused it to be a chicken. That's how natural selection and evolution work. Okay, chickens came after eggs. It's just, that's the way it is, people. Okay, all this philosophical stuff. Okay, yeah, the philosophical stuff is just dumb. Okay, Confucius got nothing on me. I got an answer for every one of his silly questions. Okay, like if a tree falls in the forest, does it make a sound? Yes, it does. When a tree falls, it forces air out of the way and makes a sound. And people, then they'll say, well, but you're not there to hear it. How do you know? Because it's physics. Okay. Nah, it makes sound waves. See, but I'm a physicist. Sound and sound waves are the same thing. Sound is a form of energy which is carried by waves. Therefore, yes, it makes a sound. Okay. It's also like, what's the sound of one hand clapping? I got nothing on you. You got nothing on me. I know what one hand clapping sounds like. It sounds like that. Okay. It's supposed to be some sort of statement on you can't be alone. You have to have two hands to clap or some stupid thing like that. I'm like, no, you don't. One hand can clap, clearly. You have to lock the back of your hand in position and then relax your fingers. You can entertain yourself with that tonight. Do it when you're by yourself, though, because if you do that while other people, they're going to think you're weird. Okay? Just like you just thought I was weird when you saw me do it. So, all right. Now, here's the other thing, guys. Depending on the situation, work and energy are going to be equal. In fact, in most situations, they're going to be equal because if I do work, I'm transferring energy to something else. If it had no energy to start with, then the amount of energy it now has is equal to the work I did on it. All right, so that's the other thing we have to know about work-energy theorem. Okay. All right, so strictly speaking, and you learned this in Science 10, work is done when a force is exerted through a distance. So if I'm pushing a stalled car, okay, I'm doing work because I'm exerting a force and the car is moving in the direction in which I am pushing it. Is it possible for me to do work using a force not directed in the direction the object is moving? Yes, it is. All right. Just not all of my force is actually doing work. All right. And we'll look at an example of that in a little bit. Okay. The key thing here, though, is you're not doing work unless there's a change in energy. So when I push this car, if I push it on a level road at a constant velocity, am I still doing work? Okay, well, we just said that work's a change in energy, right? If it's a level road, I'm not changing its potential energy. And if I'm pushing it at a constant velocity, I'm not changing its kinetic energy. Well, then I'm not changing its mechanical energy, am I? Okay, am I still doing work? Yes, I am. I'm just not doing any work on the car. Okay, the car's energy isn't changing. What I'm doing work against are non-conservative forces, like friction. Yeah. Okay, there would be friction there. Okay, in order to keep something moving at a constant speed, I have to just overcome the force of friction. If I'm on a level road, I just have to overcome friction, and I can keep that thing moving at a constant speed. It's what your cruise control does all the time. Okay, so that's what I would be doing in this situation. I'm not doing any work on the car because the car's energy isn't changing. What I'm doing work on is the surroundings. Okay, the energy of the surroundings is going to change in this situation because in pushing the car, I'm going to generate two kinds of energy: sound and heat. Okay, those are going to go into the surroundings. I will lose energy. Okay, I will lose energy to the surroundings. That still counts technically as work. I mean, technically it would be heat. I would be doing heat because I would be losing energy to the surroundings, not mechanical energy, but okay, I'm losing it to the surroundings. So I would still be doing work, just not on the car. Okay, is that all right with everybody? It's kind of weird, but it's true. And in fact, that's what most situations involve. Okay, I'm not always trying to accelerate something or lift something. Sometimes I just want it to move along with me at a constant velocity. Then all I have to do is overcome friction, okay, and it'll work. All right. Now, what's new about work is force times distance in Science 10 is this. We insert the cos of theta into this because sometimes the force I use is not in quite the same direction as the work being done or in the movement of the object. For example, if you look at the way this person is pushing on the car, it kind of looks like their force would be directed like this, kind of down and forwards on the car, all right? But that's not the way the car is moving, okay? So I'm only concerned with this part of their force, which would be calculated by taking this force times the cos of theta, because it would be finding the adjacent side. All right? Everybody okay with that? All right. I wouldn't use sine here because I'm not moving the car in which direction? Yeah, I'm not moving it vertically. Okay? It's not moving vertically, so I'm not doing any work vertically. But I am doing some work this way. Right? And I would calculate it that way, and then that would be the work done or the energy lost to the surroundings, or the work done against friction, or something like that, because I'm not changing the energy of the car. Okay. All right, so everybody kind of understand how this part works? The vertical component of my force, which is doing nothing. Well, yeah, I mean, if I was looking at this in terms of a free body diagram, okay, I wouldn't be doing any work vertically because the net force vertically and the movement vertically are zero. I would have force of gravity and my vertical force, and then F normal would push back with enough force to balance them off, right? And it wouldn't be any different if I was pulling a luggage carrier, right, or a suitcase, right? I'm pulling at an angle, but I'm not lifting it off the ground. Only the horizontal component of my force is doing work against friction. The vertical component isn't. The suitcase isn't changing its energy vertically. Friction isn't acting vertically because the object's not moving vertically. With me there? Okay. So the force that the non-conservative force I'm working against is friction, and it acts straight backwards against. Okay. All right, everybody all right with that? Okay, now here's a weird thing. Force, vector quantity. Displacement, vector quantity. Work, scalar. Energy, scalar. Work and energy are scalar quantities. They do not have direction, yet they are calculated using vector quantities. Why are work and energy scalar? Yeah, you can't. You can't put a direction on those things. Energy is the ability to do work. That work can be done on anything in any direction. So I can't put a vector on work or energy. Now, work can be positive or negative, but that doesn't have to do with direction. It has to do with whether you're doing the work or whether it's being done to you. It's a matter of, are you gaining the work or losing the work? Okay, if I do work on something, from my perspective, that's negative work because I lose the energy. From the system I'm working on's perspective, that's positive work because it's gaining that energy. Does that make sense? Okay, but other than that, there's no direction on work or energy. Okay. Okay, so these 4 girls are pushing on this rock. Are they doing work? Not on the rock, on themselves, and some energy is going to the surroundings, but they are not doing any work on the rock. Okay, because the rock's energy is unchanged no matter how hard they push on it. Okay, so if I come up to the wall here and I go, okay, if I push on the wall, okay, I'm pushing on the wall's not going anywhere. I'm not changing the energy of the wall. But if I keep pushing, I'm going to get tired. Why? The wall pushes back. If I don't brace myself against that returning Newton's third law kind of force, okay, that reactive force, okay, I'll fall over. So I brace myself, and what happens to my muscles when I push? Okay, they contract, which means they get smaller. There's your distance. Force times distance. My muscles get shorter by a certain amount. There's a force that's causing that. There's the energy. Okay, that energy is just going to be heat. Okay, sound, whatever, it's going into the surroundings. I'm not changing the mechanical energy of the wall. My mechanical energy is not really changing. I mean, a little bit, my muscles shorten. Okay, but for the most part, I'm accomplishing nothing. Okay, it's like if you're Sisyphus. Okay, you guys know who Sisyphus was? Yeah, in Greek mythology, he was condemned by Zeus to push a rock up a hill for all eternity. Okay, except it was so big he couldn't move it, so his whole life would be pointless for all eternity. It'd suck. Yeah. On your mass, okay, because your mass is going to have a change in its potential energy, right? You start out on the ground in a push-up. Your mass has no mechanical energy. You're not moving and you're on the ground. As soon as you push, you are now higher above the ground. Okay? If you do that at a constant velocity, you have only changed your potential energy. If you push really hard and fly off the floor, then you can do the clap, then you'd be changing both kinetic and potential. Does that make sense? Yeah. We're actually going to do a bench press example here in a few minutes. It kind of works the same way. Okay, now units for work and energy are joules. Okay, and a joule, okay, if we look at work is force times distance. Okay, force is measured in newtons, distance is measured in meters. So a joule is a Newton meter. Remember also that a Newton is a kilogram meter per second squared. Multiply that by meters, we get kilogram meters squared per second squared. Those are the fundamental units for a joule, a kilogram meter squared per second squared, okay? Or a Newton meter, or just write J because it's joules and that's easier, okay? But you do still need to know the fundamental units there, okay? All right, questions on the units? All right. So let's just confirm here, guys, because we got all kinds of different formulas that calculate energy, right? We got potential energy, okay? EP equals M times G times H. So that's kilograms times meters per second squared times meters. Yeah, that works out. Okay, that gets kilogram meters squared per second squared. All right, what about kinetic energy? Okay, so mass is in kilograms and speed squared would be meters squared per second squared. Yeah, that works out. That gives me kilogram meters squared per second squared. Okay, so we got these formulas. They all still give us the same units, joules. Okay, kilogram meter squared per second squared. Okay. All right, so here's where this cos of theta thing comes in. We kind of talked about it already, but if I'm pulling this luggage carrier, this cart or whatever it is, okay, and I'm pulling at an angle, the cart is not moving in the direction that I'm pulling. It's moving horizontally. Right? So am I changing its potential energy at all? No, because I'm not counting the part where I picked up the cart, just where I'm pulling it. Okay, so I'm not changing the potential energy of the cart because the cart's height isn't changing. If I pull it at a constant velocity, then again, its kinetic energy is also not changing, because in this situation, the net force would be Zero, right? I'm pulling this cart along the floor at a constant velocity. I'm exerting a force only because there's a force of friction acting backwards, and I have to do work against it to overcome it. Okay? So if I wanted to calculate how much work I was actually doing against the force of friction, I would need the horizontal component of my force because it's working against the force of friction, and they would be equal because it's not changing its velocity. Everybody okay with that? Right, so all I have to do then is plug into my formula where work equals F cos of theta times d. Okay, so I would be, as long as I knew the force and I knew the angle and I knew how far I was going to pull it, I'd be able to calculate how much work was done. Okay. Now, is it going to be a lot? No. Okay, I mean, especially when you got wheels. Like this would be a lot more difficult if this was all that mass being dragged along the floor. Okay, then friction would be a lot greater. Okay, and you'd get more tired. Okay. All right, so here's our example. I have a 45 Newton force in that handle. The handle is angled 50 degrees, and I'm pulling the cart 75 meters. All right, so I just plug my numbers in. Okay, F was 45 newtons. Theta was 50 degrees, and the distance is 75 meters. All right, when I plug that in, I find that it takes 2.17 times 10 to the 3 joules worth of energy. Okay, that sounds like a big number. That's 2.17 kilojoules. It's like 2.5 calories. Okay, so you're not burning a lot of calories pulling this luggage cart for 75 meters. Okay, better find some other cardio to do. Okay, if you're looking to burn some calories, that's not getting it done. Okay. Everybody all right with that? Okay. Bench press example. I watch people work out, and I think it's funny. Not because working out is funny. I love doing that myself. But okay, I like watching people do it wrong because then I feel superior. Because I don't know, that's just a weird thing, but whatever. Okay. But a lot of people, especially on the bench press, are just not getting the most out of their workout because they'll slap a bunch of weight on the bar, work like crazy to get the bar up, and then they'll just let it come back down. Okay. They won't push on it as much when it comes back down. Okay. And if you do that, you're only getting half the workout because you have to exert the same amount of force to lift the bar as you do to lower it if you're lowering and lifting at a constant velocity. Okay. A lot of times what happens with people that are doing light weights is they push too hard and they actually accelerate the bar, and then when they get to about here, they just let gravity slow it down. Okay, which means they exerted a force, but not over the full distance. Okay, so they don't get as much out of their workout by kind of jerking the bar upwards. You want to lift the bar slowly, and then you want to lower it back slowly. Okay, that means you do more work and you get more out of the workout. Right? But let's look at this from kind of a physics perspective. The barbell weighs 710 newtons. So how much force do I have to exert to lift it? 710 newtons. If I'm going to lift it at a constant velocity, I have to exert the same amount of force upwards. All right. Now, the barbell is moving in the same direction as the force is exerted in the same direction as the barbell is moving. All right. So what's theta in this case? 0. Right? There's no angle between this and this. They're parallel. All right. So then I would just do this. Okay. Work equals F cos of theta times d. Okay. But that's going to be 710 newtons times the cos of 0 times 0.65 meters. What's the cos of 0? 1. Okay, the cos of 0 is 1. So it's really having no effect, right? I'm multiplying by 1, doesn't change anything. All right, so I would be able to calculate pretty easily then how much work is done here. I think it comes out to 461 joules or something like that. Okay, if we multiply it out. 461.5? Okay, so 462, whatever. 461 joules. If I now lower the barbell, what's happening to the energy of the barbell? Right, it's losing it. Okay, it gained energy when I lifted it. I did work on the barbell. I lifted it. I gave it a bunch of potential energy by lifting it. Okay, 461 joules worth. Now I'm exerting a force on it, still up, still the same force, but now it's moving downwards towards me. Okay, so from the barbell's perspective, it's now losing energy. Effectively, it's doing work on me now. Okay, now that work is just going to turn into heat and stuff. But okay, if I dropped it, it would really do work on me. Right? It would change my shape in an undesirable way. Okay, I wouldn't want that. Yeah, I'm definitely sure about that. Dropping a big heavy barbell on your chest will cave in your chest, so you don't want to do that. Okay, but it would because it's got a lot of potential energy, and I gave it that potential energy. So what I want to do is lower it slowly. Okay, and let that energy just kind of go away. But then that energy from the barbell's point of view should be positive or negative. It should be negative. It's going to have less mechanical energy when I lower it back down. So when I calculate that, okay, I'm going to go work equals still force times the cos of theta times d. But now what's theta going to be? Nope, my force is still up. To lower this barbell, I still exert a force upwards. Right, the angle will be 180. See, now the direction is opposite the direction of the force. It's 180 degrees. What's the cos of 180? -1. Right? So now when I go F times the cos of 180, I get force times -1 times 0.65. And now I get this same number, but now it's negative. Right? See how physics always works? It's awesome. Okay. All right. So that's like 4 slides worth of stuff that we just talked about there. Okay, so that's what we just did, the -460 there. Okay, so things we have to remember about work energy theorem. Sorry, Kevin. Oh, they use S for displacement in the book I took those diagrams from. Yeah, S stands for displacement. All right, so in order to do work, you have to have energy. Okay, work is a change in energy, okay, or it's a transfer of energy or whatever. So you have to have it in order to give it away. You can't get an energy loan, okay? You can't give away what you don't have, so you have to have that, okay? So that's the work energy theorem, okay? And these are some of the formulas. We already wrote them down and talked about them. They're on your formula sheet, okay, that we learned last year. All right, so we're going to look at a few examples here of work energy theorem today, some that are going to be pretty easy, straightforward kind of things, and then we're going to look at some where they're not actually a whole lot harder, but they involve changes in both potential and kinetic energy at the same time. Okay. So we will start out with question number 1. Okay, we'll do question number 1 together here. So I've got a sled that I'm pulling along a horizontal surface, okay, applying a force of 620 newtons. Right, so my force is 620 newtons, okay, at an angle of 42 degrees, okay, above the x-axis, or above horizontal, they said. I'm just going to write above x, okay. How much work is done if the sled is pulled 160 meters? So I'm looking for work, and I know that the distance is 160 meters. Is this one pretty straightforward? Yeah, I'm just going to plug into the formula, work equals force times the cos of theta, okay, times d, because really what I've got going on here is this. This is 620 newtons, okay? This is my 42-degree angle. The sled is moving this way, so I only need this component of my 620. Right, so when I plug in my numbers, okay, I will have 620 times the cos of 42 times 160 meters. All right, that's a lot more work. Okay, but I mean, it's a sled. It must be a pretty heavy sled. Okay, so it's a lot more work than the rolling luggage carrier that we used before. Of course, that rolling luggage carrier only required 45 newtons worth of force. This requires 620. It's obviously a lot bigger and heavier, okay, than that one was. All right, everyone follow what we did there? Okay, I want you guys to try 2 and 3. Okay, don't worry about 4 for right now. Just try 2 and 3 for right now. Okay, so with number 4, I've got this bungee jumper who jumps off of a bridge, because that's what they do. Okay, they're in free fall for 20 meters before the cord starts to stretch. Okay, it's only when the cord starts to stretch that you're changing the mechanical energy of the falling person, right? Because you're slowing them down. You're taking away some of their mechanical energy. While they're in free fall, all that's going on is gravitational potential energy is being 100% converted into kinetic. Okay, that's why the mechanical energy is not changing. All of the potential is becoming kinetic during free fall. Right? That's why there's a bungee cord. Otherwise, you just keep converting it into kinetic energy, and it would be very bad when you got to the bottom. Okay, we want the bungee cord to do work, or for us actually to do work on the bungee cord and stretch it out. Okay, that's what slows us down. It takes work to stretch the bungee cord, and that reduces our speed. Okay? So what we want to figure out here is how much work does the force of gravity do on the jumper before the cord begins to stretch? Well, when gravity is doing work, really all that's happening is potential is being converted into kinetic, which means there's a change in the potential energy during that time. Okay, so what we have is, here's the bridge. Okay, here's 20 meters below that, and then I don't know where the ground is, but it's below that. Right? So we want to calculate how much work is done between here and here. Well, we know that the potential energy is changing during that time because the height is changing by how much? 20 meters. All right, so all we really have to do here is go 60 kilograms times 9.81 times 20 meters. Right? We could say negative 20 meters here as well, because I mean we are actually descending 20 meters, and that would give us a negative number, which would be okay because that would be potential energy lost / converted into kinetic energy. Right? So when we do that, we should get 1.1, I think it's 11,772 joules, okay, worth of energy during that fall, okay, during that time. That's a lot of kinetic energy. That's why the bungee cord is there. Okay? We wouldn't want that much energy. Okay? When we got to ground level, that would be bad. Okay? That making sense? All right, I'm going to give you a 5-minute break, and then we're going to work on this one, where both kinds of energy change at the same time. It's really not as hard as it looks, but I'm going to give you a 5-minute break before we try it. Yep. All right, so in this question, I am accelerating this block up the ramp. Clearly, work is being done because that would require a change in the object's mechanical energy. Not only am I making the object go higher, which would be a change in potential energy, I'm also making it go faster, right? So I'm changing both its potential and its kinetic energy. So just in reading that question, I know right away that this is a work energy theorem question where the mechanical energy of the object is being changed by the work being done. Okay, so what I know is I know the mass of the block, I know how much the height changes or what the height change is, and I know what the initial speed and final speeds of the object are. Right? So I'm just going to start setting it up here. I'm going to start with this. Work is a change in mechanical energy. And then each step after this, I'm going to expand this delta EM out further and further and further until I've got it to the point where I can actually mathematically solve it. Right? So I'm going to say here that work equals then, if it's a change in mechanical energy, that it's mechanical energy final minus mechanical energy initial. Okay? Still saying the same thing, I've just expanded it out. Then I'll expand it even further by saying, all right, mechanical energy is potential energy plus kinetic energy. Right, so I have my final potential plus my final kinetic will give me my final mechanical, okay? And my final or initial potential plus initial kinetic will give me my initial mechanical. Right? Still saying the same thing, just expanding the formula out. Now that you look like you don't like what I wrote. Oh, EPF plus EKF. Sorry, my penmanship is terrible. Okay, EPI plus EKI. Right? And this is EMF and EMI up here. EMF, EMI. All right. I'm going to expand it even further. Now I'm going to put the formulas in that will actually allow me to calculate these different variables. Right? So work is going to be m times g times h final. I'm taking my time so you can read it. Okay, plus 1/2 mvf squared. All right, so still the same thing, but I put in the formulas for each of these energy types. And I'm going to subtract the initials. So m times g times h initial plus 1/2 mv initial squared. Height. All right, so here's my final formula. After this, I'm plugging numbers in, okay, because I've actually got all the variables now identified. There's no way for me to further expand this out. So now what I need to look at is, what are some of these numbers? So given the situation here, I'm starting at the bottom of the ramp, moving at 1 meter per second. So do I have kinetic energy at the bottom of the ramp? Yes, because the box is moving at 1 meter per second. What do I not have at the bottom of the ramp? Right, I don't have any potential energy because at the bottom of the ramp, the initial height would be 0. All right, so there's one less thing for me to have to plug into my formula.
I don't know if this is like nitpicky, but like at the bottom of the ramp, it's on an elevator above the ground.
You're right, that's nitpicky. We're going to say it's at the bottom of the ramp. No, you're absolutely right. It really should be kind of here, right, where the height would be 0. Yeah, I mean, it does say at the bottom of the ramp. At the bottom of the ramp, the height is 0.
Yeah.
You're right. The center of mass of that mass is not 0, but we're going to say it is.
All right.
Yeah, you're right. The diagram is lying. I can cancel the m's in a law of conservation of energy question if I'm solving for an h or a v, because those are not dependent on the mass. All things accelerate at the same rate. Because I'm looking for joules, I can't take kilograms out of here, or I won't get joules. Yeah, does that make sense? Because yeah, you're right. In Science 10, we would cancel the mass because mass was in every term. Mass isn't in this term, right? That's force times distance, so I can't cancel it. Okay, but no, that's a good point. It often comes up. All right, so now I know I don't have any initial potential energy. Now I can plug in my numbers. So I'm going to go 1.2 kilograms. Okay, so my initial, or my mass, which is the same everywhere, times 9.81 times my final height, which they told me is 0.850 meters. Right? And then I'm going to add on to that 1/2 times 1.2 times my final speed, which they told me was 4 meters per second. Right, so there's my final mechanical energy. Now I need to subtract my initial mechanical energy, which is all kinetic, and there's not very much of it. Right? So there's 1/2 times 1.2 times 1 squared. Okay, now you kind of realize why I say there wasn't very much of it. Okay, that's not going to be a very big number. 0.6 times 1 squared is 0.6, right? It's not very much. Okay. All right. So when I plug all of this in, okay, I'm going to find that this is 19.6 here, I think. So we'll just plug it all back in. But so we have 1.2 times 9.81 times 0.85 plus 1/2 times 1.2 times 4 squared. All right, so at the top of the ramp, the box has 19.6062 joules worth of energy. Now I need to subtract how much energy it had at the bottom. So that'll be 0.5 times 1.2 times 1 squared. All right, so I have to do 19 joules worth of work in order to accelerate this box up this frictionless ramp. Okay. If friction was involved, where would I put it? If friction was involved, where would I put it? Yeah, I would have to add it in here, right? Okay, like I would have, here's my final energy, and I'm subtracting the initial, but the amount of, I would have to do more work if there was friction, right? So I would have a, like, plus the force of friction times distance over here to calculate the work I would do against friction. it would be added in there. I would have to do more than 19 joules worth of work if there was friction on the ramp. Okay, so it would be an added, what we call work against a non-conservative force. Okay. All right, so what we end up with here is 19 joules worth of work. All right, now this could go basically any number of other ways. Like this is about as straightforward as they would get. Don't get scared. Okay, but like I could have just as easily said, you know, the ramp is this long, how much force would be needed? Okay, and then instead of having work here, I would have force times distance here. Okay, and then I would calculate, yeah, it was a good save. Okay, then I would just divide both sides by d and calculate the force. Okay, or I would say 19 joules worth of work are required to accelerate a box initially at 1.0 meters per second up this ramp. What's its final speed? Okay, so then I wouldn't have this. I'd be solving for VF instead. And it would be like manipulating a law of conservation of energy problem. I would just isolate VF.
How do you manipulate something when it's like equations? I don't know how.
Okay, well, let's look at it. Let's say I want to solve for VF. Okay, so I'm just going to kind of copy that back out again. So work will be m times g times hf plus 1/2 mvf squared minus 1/2 mvi squared. Okay, I want to solve for VF. First thing, add this. Right, I'm going to add it to both sides so that it's gone. Right, so I'll have work plus okay, I still want to get VF by itself. What can I do with MGHF? Subtract it over to the other side. Okay, so I'm going to have work plus 1/2 MVI squared minus MGHF equals 1/2 MVF squared. All right, divide both sides by half of M. And yeah, there's a lot of moving around for sure, but it's nothing you guys haven't done before. Just algebra. Yeah, it takes a while for sure, and then you kind of got to think it through a little bit, but definitely possible. You guys can do that. Because I would be looking for the force going up the ramp. It would have already been parallel to the distance. Theta would be 0 in that case, because the force I would be finding would be in the direction it was going. So I just took it out automatically. I could put it in there, but it's 1. Cos theta is 1 on that one. Yeah? Okay. Everybody all right with those? All right, try number 1 here. I think we got time to do number 1, maybe even number 2. Okay, so we'll try number 1 here. We started on number 2 in period 2. We didn't quite finish it, so let's get number 1 done and see how we do on that one. So let's have a look at number 1 here. Anybody ever done any rock climbing or rappelling? Okay, like rappelling is a lot of fun. So you back over the mountain, the edge of the mountain, and you just kind of jump off the face and work your way down. Okay, if you do that right, then you are reducing your mechanical energy on the way down. Okay, you have a lot of mechanical energy in the form of gravitational potential energy at the top of the cliff, but obviously you don't want all of that when you get to the bottom, and that's what we've got in this situation. Okay, their energy at the top is all potential. Their energy at the bottom is all kinetic, but they're not equal. They would only be equal if they did what? If they fell. Right. If they fell, then their kinetic energy at the bottom would be equal to their potential at the top, and that wouldn't be good. Okay, so what they have here is a situation where they're rappelling. And when you're rappelling, you have a rope going through a carabiner, okay, which is like a metal clip. All right. If you've ever done this, you learn this lesson really fast. Don't try to hold on to the rope, okay, and don't touch the carabiner when you get to the bottom. There, it's hot. It's like raging hot, okay? Because the rope has been sliding past it, and it's the friction between the rope and the carabiner that keeps you alive. That's where all your mechanical energy goes. It gets turned into heat from the force of friction between the rope and the carabiner, okay? So when you're rappelling, okay, you have one hand on the rope in front of you, and you have one hand on the rope kind of behind and below you, and as you change the angle in that rope, it allows it to pass through the carabiner, okay, or through the brake, okay, and a person above may also be belaying you, which is kind of lowering you, right? So that's what we got going on there, but we want to obviously lose or have our mechanical energy do a lot of work on the carabiner and the rope. Okay, so we're going to say that the work here is the change in mechanical energy. At the top, okay, we have obviously mechanical energy, okay, in the form of potential, and at the bottom we have mechanical energy in the form of kinetic. So really all we have is this. Whoop, not 1/2, sorry. Initially, I'm not moving, but I'm very high off the ground. At the end, I'm on the ground, but I'm moving at some speed. Okay, there's definitely a change between the energy here and the energy here. All right, so all I have to do is plug in my numbers. 1/2 times the mass, which was 72 kilograms, times 5 squared, the speed at the bottom, minus 72 times 9.81 times the initial height, which was 25 meters. All right, so 0.5 times 72 times 25. Whoop, 0.5 times 72 times 25. Okay, so there's my energy at the bottom. I'm going to subtract the energy at the top. All right, so I get a negative number. Is that okay? Yes, I've lost mechanical energy. I have way less of it at the bottom, and that's a good thing. Okay? I have 1.68 times 10 to the 4 joules less energy. That's how much work was done on the rope and the carabiner and whatever else was lowering me down, okay, to the bottom of this mountain. Okay.
Like the carabiner has the energy that you're putting onto it. The question is asking what's the work done by the client
On the rope. So we're saying the rope slash carabiner. Yeah. The rope is also going to get hot. I mean, if you've ever tried to like hold onto a rope and slide down it, you get rope burn, right? Well, it's the same thing. Yeah. So what we're saying is there. I mentioned a carabiner. That's not mentioned in the question. They're just saying the rope. Yeah. Nobody repels like this. You're just holding on to the rope. That's how you get, well, nylon slivers and burnt hands. Yeah. Okay. I want you guys to have a look at number 2 here. Okay. We've got a force of 150 newtons up, acting on a 9 kilogram mass, lifting it to a height of 5 meters. Okay, so first part of the question, part A, super easy. Just calculate the work done. Okay, then calculate the change in gravitational potential energy. Also fairly easy. Then hopefully we'll get a chance to talk about what this part C is looking at. Okay, so if we want to calculate work done, we take 2 numbers and multiply them together. What are they? Force and distance. Okay, so we got 150 times 5 meters. All right, so to calculate that first part, okay, we just go 150 times 5. All right, so the total amount of work done is 750 joules. Okay. Then it asks, what's the change in gravitational potential energy? Well, the change in potential energy would be m times g times the change in height, which is 5 meters. All right, so I'm going to take my 9 kilograms times 9.81 times 5 meters. That's not going to be 750. Times 5. 441.45 joules. Okay, so the question, the way it's worded is a bit misleading. It says I lifted this thing. More than likely, I didn't lift it, I threw it. Because I did 750 joules worth of work, and only 441 of that was needed to raise the object. So this thing didn't move at a constant speed, it accelerated upwards, which means I didn't just change its potential, I also changed its kinetic. Okay, I threw this thing up in the air. Can I calculate its change in kinetic energy? Yeah, it'll just be the leftover, the difference, okay, between the total work and the amount of work required to change the potential energy. So here's the thing you got to realize. I did more work than was necessary to lift this, which means there was a net force. It's the net force that changes the kinetic energy, because net forces cause objects to accelerate. Okay? If you're going to change kinetic energy, you have to change the speed. So net force changes the kinetic energy while the balance changes the potential. We'll talk more about that tomorrow. No quiz tomorrow.